So for this homework, we're taking a different approach to Hardy-Weinberg. So just like the questions in your homework, we start here with a puzzling observation. So we can see from this observation that this place, Nepal, is heavily affected by malaria. We also see the second bullet point here, Tharas people are native to Terai. They have some form of innate resistance to malaria, and that the non-Taurus people who migrated to Terai over the last century have a high incidence of malaria infection. So read over those three again, think about why this could be. I want you to come up with a hypothesis and try to explain why this is. So after you've paused the video and taken a minute to come up with a hypothesis, next I want you to pause the video again and come up with a feasible way to test this hypothesis. So now that you've come up with a hypothesis and a potential experiment, let's look at what the lab's true hypothesis and their designed experiment look like. So the lab that conducted these experiments, they hypothesized that there is a genetic cause with the Tharas people having some gene that is inferring resistance, and that is resistance to malaria. In order to discover if this was possibly the case, they designed this experiment to compare the genes of the Tharas with the non-Tharas people living in Terai. So when they compared the genes of the people in Terai, this is what they discovered. So if the people in Terai were all one population in Hardy-Weinberg equilibrium, what pattern would you expect for their genotypic frequencies? Take a minute to think about that. The answer is that we would expect their genotypic frequencies to be the same in both the Tharu here and the non-Tharu people that are living here if they're in Hardy-Weinberg equilibrium. So given the genotypic frequencies that we see here, let's calculate the allelic frequencies for each population. So let's start with the Tharu Western population. So because you've already calculated genotypic frequencies before, I'm not going to go through every step. But to kind of break this down to be a little helpful, we see that 10 people in the Tharu Western population have the heterozygous genotype big A little a. So this means that there's 10 big A alleles and 10 little a alleles. Also we see that 8 people have the little a allele, which means that in those 8 people there's 0 big A alleles and that there's 16 little a alleles. So we can see that in total there are 36 alleles, 26 of which are little a's. So if we do the calculations that we've already learned, we find that the q value is 0.72, and then the p value, which is just 1 minus q, was 0.28. Now pause the video and see if you can calculate the genotypic frequencies, the allele frequencies for each of these populations. So through central, non-through western, and non-through central. So pause it and calculate the p and q values for each of those populations, and then I'll put them up and you can compare. These are the p and q values, or allelic frequencies, that you should have gotten for each population. Now let's compare the allelic frequencies that we calculated here on the left with what they actually calculated in the experiment. So if you look closely, you can see that they're all exactly the same. So for the Tharas Western population, a p-value of 0.28, q-value of 0.72. The Central Tharas, q-value 0.83, p-value of 0.17. The non-Tharas Western, q-value of 0.03, p of 0.97. And then finally the non-Tharas Central of a q-value of 0.09 and a p-value of 0.91. And so our calculations are exactly the same as what they calculated in the lab. So we know from earlier in the question that the Tharas people have a greater resistance to malaria than those that are non-Tharas. So from what we've done here, there should be enough information for you to figure out and start hypothesizing why that is. So take a minute and look at these allelic frequencies and think of what might be a possible explanation for why this occurs. Those who conducted this experiment found that the little a allele, which as we can see, as we've calculated, based on this Q value, is much more prevalent in those Tharas people. So the little a allele makes the people with its immune systems work faster so that they don't get symptoms of malaria. So this is a great example of natural selection at work. So take a minute to think about the people that would be living there and the effect that malaria has on those people. So if you started with people that half of them were big A, and didn't have this little a with the resistance to malaria, and half of them were big A, little a, and then malaria struck, and most, if not all, of those that didn't have a little a, so big A, all of them died, leaving only those with the big A, little a to reproduce. So then that little a gene is passed on, and it changes that genotypic frequency that we would have seen before. And so generation and generation and generation go by, and that little a allele becomes more prevalent. So as that little a allele becomes more prevalent, it leads us to one final question. What kind of selection is this? Take just a couple minutes to think about this. So because natural selection is pushing towards homozygous little a alleles, that means that this is directional selection.